Okay, so the third paper is going to be an online presentation. The title is Neuron3Points, learning to generate physically realistic full body motion for virtual reality users. And it's going to be presented by Jongrin Ji. I hope I said that correctly.
Yeah.
Yeah.
Okay, I'm Yongjin Ye from University of Chinese Academy of Sciences, and I'm currently a PhD student. For better presentation, we pre-recorded the narration for our slides.
In recent years, with the development of virtual reality technology, consumer-grade VR devices have become very popular. A typical VR device mainly consists of a head-mounted display and two handheld controllers, which help users to observe and interact with the virtual world in various VR applications and games. However, current VR applications usually only project information about the head-mounted display and handheld controllers into the virtual reality world. Due to the absence of full-body information, the user's experience is greatly reduced. Tracking the full-body movement of a user in real time and animate an avatar that can reproduce the user's actions through VR device is a plausible way to fix this problem. However, while it is relatively easy to compute good quality upper body movement when the user is sitting or standing in place, predicting plausible footsteps and lower body motion is usually very difficult when the user needs to move around. The motivation for this work is to generate natural and physically realistic full-body motion from only 3 VR trackers when the user moves around, and also hope that the global tracking accuracy between the input VR trackers and the corresponding body parts is guaranteed. Synthesizing interactive human motions using low-dimensional control signals such as a keyboard or game controller, has been a long-term topic of character animation. Data-driven methods have been proven to be an effective way to generate high-quality interactive character animation. Unlike data-driven methods, physics-based approaches explicitly incorporate physics simulation into the motion generation pipeline, which ensures physical accuracy of the generated motions and allow response to unexpected perturbations. Our work takes benefit of both the data-driven approaches and physics simulation to achieve physically realistic motion generation. On the other hand, reconstructing full-body human motions using a small number of sensors or markers becomes more and more demanding. Given the popularization of VR or AR devices, many state-of-the-art approaches achieve this goal using 6 body-worn sensors on the user's head, limbs, and waist, which does not directly work with the out-of-box components of a typical VR system. Research on estimating full-body human motion using even fewer tracking signals remains relatively sparse, where a sensor mounted on waist is often needed to reconstruct root transformations. Deep Motion offers a physics-based 3-point full-body tracking solution. Their technique is based on a simplified control model, and the simulated avatar can look robotic. Unlike those approaches, our method enables natural and physically plausible full-body tracking using up to 3 VR trackers, which is compatible with typical commercial VR systems. Here is the system overview of our work. Our system is composed of 4 major components operating at different time scales. The full-body pose predictor module reads the transformation signals of the VR trackers and predicts the full-body pose, as well as the location and heading direction of user according to the current state of the avatar character. These estimations can then be used to update the character's pose directly. We refer to this updating strategy as the direct mode of our system. To create a physics-enhanced user experience, we employ a full-body control policy module to take the estimated poses as a reference and compute a target pose that will be used to actuate the character to track the user's action. At runtime, the full-body pose predictor and control policy work jointly as a combined control predictor. The simulation module performs physics simulation and updates the state of the character. Finally, an additional track position correction module is involved to encourage simulated character to follow the VR trackers accurately. Here is the main results of our work. Our data-driven physics-based system simulates an avatar character that can mimic user actions in the virtual world in real time. After explaining how the whole system works, we now introduce the main components of the system separately. When using a VR application, a user's upper body typically exhibits higher range of motion than their lower body, and the movements of the upper body and the lower body are not always strongly correlated. To deal with such degrees of freedom, we consider our character as two disjoint sets of joints and treat them separately. As shown in the figure, given the previous estimated heading transformation and the current VR tracker input, signal predictor first transfer the VR input into the control signal for lower body predictor. Lower body predictor then predicts the coordinate leg motions and updates heading frame. Upper body predictor then computes an upper body pose that follows the tracker's position in the updated heading frame. Combining two pose predictor, we can obtain the full body pose in the predicted heading frame. Given a sequence of VR track input, an initial state of the character and initial heading transformation, the pose predictor generates a series of states autoregressively, as shown in the video. Our predictors have similar architecture, so we take signal predictor as an example to introduce the details. It is implemented as a recurrent neural network consisting of 3 GI layers combined with one layer fully connected encoder and decoder layers. As for the output control signal Z, it consists of the centroid position, velocity, and angular momentum of the character's upper body, as well as the change of heading frame. The control signal Z is then used to generate lower body motions. The MSE loss terms are weighted mean squared error between the quantities represented by the subscripts and their corresponding ground truth. When training the signal predictor and the lower body predictor, an heading loss term is used to minimize the error of the estimated global heading transformation, computed by accumulating the sequence of predicted change of heading frames. In addition, a forward kinematics loss is added to ensure consistency between the predicted joint orientations and joint positions. We employ a two-stage training process to train the pose predictor using the motion capture data, where each sub-predictor is pre-trained separately, then fine-tuned jointly. The full-body control policy module converts the estimated full-body poses of the user into target poses, which will be used to actuate the simulated character using PD servos. We pre-train the full-body control policy using reinforcement learning on our motion capture dataset. The reward at each time step includes 6 components. The pose reward R-pose encourages the character to match the reference pose locally. The link orientation position reward penalizes the global tracking errors. In terms of the positions and orientations of the character's bones, the balance reward encourages the relative position between the character's feet and its center of mass to match those from the reference, which helps the character stabilize his pose and maintain balance. The contact reward penalizes the differences between the position of the character's foot and its reference when the foot is in contact with the ground. At last, The foot height reward encourages the character to lift its feet to clear the ground when moving. We employ an adaptive state initialization strategy which encourages the training process to start a rollout from a less visited state to mitigate the problem that the training may overfit to the motions that are easy to learn when choosing random initial states uniformly. Also, we pre-trained the control policy by imitating the tracking controllers, optimizing by Samgong algorithm, which significantly accelerates the training at the early stage. We train the control policy using the PPO algorithm, which alternates the collection of simulation rollouts and the policy update. After pre-training the full body pose predictor and the control policy, our system fine-tunes them together as the combined control predictor. The same rewards as pre-training of full body control policy are used in this fine-tune process. The motion generated by the pose predictor is used as the reference for the rewards until the training process has plateaued. To prepare for unpredictable movement from users, a little delay in the tracking is allowed. When every 3 frames of tracker input are received, a signal force-cutting strategy is involved to predict 6 future frames of the input. The full-body pose predictor then takes these extended tracker inputs and predicts a short motion clip of 9 frames recursively. To ensure accurate tracking of the VR trackers, we employ an additional tracker position correction module in our system. This module applies virtual forces on the avatar's hands to correct their position. These virtual forces are not directly applied to the hands of the simulated character. Instead, the character tries to realize such virtual forces using joint torques, which are computed using Jacobian's transpose control. We demonstrate a variety of examples where a user plays in VR with our system. In this scene, the user can move freely in the VR environment given the VR inputs. Several virtual mirrors are placed around the users so they can check the action of their virtual avatar in real time. The first-person point of view is shown in the top right. This scene is a minigame where the player needs to move and animate randomly spawned objects by touching them. In this scene, the participant is asked to rearrange objects of different shapes and move those of the same color together. In this scene, we put several simulated objects around the character. The user can interact with these objects by stepping on or pushing them. Here is a comparison between direct mode and normal mode. The direct mode has better tracking accuracy while suffering from unstable foot stepping and foot sliding occasionally. In contrast, the normal mode is more robust to unseen input and has much more stable foot stepping. But it has a little bit of delay and less tracking accuracy. The first-person point of view can be checked in the left lower corner. To validate our decoupled network architecture design, we compared the performance with 2 baseline networks, a RNN-based full-body pose generator and a phase-function neural network. The assessment is based on the contact accuracy measured as the amount of foot skating. In this experiment, we considered both the contact label predicted by network that computed based on the height of the foot. The results show that our pose predictor generates motions with more stable foot contacts than the baselines, indicating that our decoupled network architecture is more robust to unseen up-body input. We demonstrated the capacity of one-point tracking with only a head-mounted display by removing the signals of 2 handheld controllers from the VR tracking input and replacing them with the corresponding predicted signal. As shown in the video, our system successfully reconstructed plausible full-body poses using only the HMD input. Here is comparison of the results with or without tracker position correction. We can observe that with tracker position correction, the input trackers match the corresponding body parts better. We demonstrate two main contributions of our work. First, we build novel real-time full-body motion tracking system that generate physically realistic motions from sparse VR trackers. Second, we develop a full-time motion predictor module with decoupled upper-body and lower-body pose predictors. We find this network architecture performs better than the baseline methods and is more robust with respect to unseen upper-body motions. However, our method still have several limitations. First, our system only predicts lower body motions that are the most probable according to the upper-body VR trackers. Special lower body motions such as kicking are hard to predict using such limited information. Second, where our decoupled pose predictor module is robust to unseen upper-body motions, the performance of the lower body pose predictor is still limited by the training data. Third, the normal mode of our system has a small amount of time delay. Reducing it to a more acceptable level will be a goal for future research. And lastly, our full-body pose predictor and control policy are trained based on the same simulated character. Generalizing our system to support users with different body ratios and simulate non-human avatars remains a future work.
Okay. Thanks for the presentation. So we have now time for a few questions.
Hi, thanks for your presentation. I have a question about the, well, a couple questions actually. One about the pre-training phase. So I see that you're using SAMCON to do some of the pre-training. And I was wondering why you're using SAMCON there. It's really designed for like contact rich motions. It's a fairly heavy process, but a lot of the motions that you're showing in the results are really contact rich. I was kind of curious if this is a necessary part of the pipeline.
Oh, sorry, I can't hear you clearly.
You want to come over here? Why? Before we go to bed? Yeah. I don't think that's all.
Yeah, you can just plug it in here.
Hi, so thanks for your presentation. Can you hear me now?
Yes.
Great. So my question was about SAMCON and the use of SAMCON during the pre-training phase. And I was wondering if this is a really necessary step, because SAMCON is really meant for like contact-rich motions. It's a fairly heavy framework, and I was wondering if this is a necessary part of the pipeline.
It's not necessary for our training, but we use it just to save time, because our system training costs a lot of time. The whole system training will cost about 5 to 6 days or more longer. So we pre-train our policy for the better initialization.
Oh, okay, thank you. And I have one more question. The question is about jumping and ballistic motion. So is it possible to do ballistic motions with this tracking framework?
I believe it is possible, because but we do not capture the jumping actions in our data set, so we now cannot reproduce such actions. With the capture data of jumping, we think it is possible to reproduce such actions.
Do you also calibrate the mass of your model that you're using?
Can you say
Do you,
it again?
do you calibrate the mass of the model you're using to the person that's being tracked? Your physics-based model, does the mass match the person that's being tracked?
Yes, yes.
Thank you.
Mm.
Any other question? Actually, I have one quick one. So in your pipeline, you're using the tracker's position at the end to introduce a correction so that you can reduce the positional drift that you get at the end. Why not including it in the loss function, just the distance between trackers and the end effectors to maybe train the system to reduce also that error?
We have also tried that method, but it does not improve the quality too much. So we just apply this component when at runtime.
Okay, so it reduced the error a bit, but not enough. Is that what you're saying?
The tracker pricing correction module, we have tried to use this module at training time, but it does not improve the performance too much. So we just implemented this module at runtime.
Okay, thank you.
Mm.
All right, so anybody else has a question? No? All right, then thanks for the presentation, and we can.